Welcome to our course. In this video, we'll explore the architecture and specialized IP addressing concepts within Prisma Access, starting from the ground up. Let's get started. Today, we are diving into the core architecture of Prisma Access, focusing particularly on how it handles IP addressing. Think of Prisma Access as a powerful, cloud-based bodyguard for your company's network. It is built on the Secure Access Service Edge, or SASE concept. Prisma Access delivers top-tier network security features, like advanced URL filtering and threat prevention, directly from the cloud as a security service edge solution. This is a critical point. It operates as a cloud-native framework that blends networking and security features into one comprehensive service. Palo Alto Networks handles the management of this massive, worldwide security infrastructure for you. The primary goal is simple: to secure mobile users and remote office locations whenever they connect to the internet or corporate applications. This cloud approach ensures that consistent security policies are enforced no matter where your users are physically located in the world. We will explore the components that make this global security possible. What did we learn? We learned that Prisma Access is a global cloud-based security service, SASE, managed by Palo Alto Networks. The important point is that it handles all traffic inspection and security policy enforcement consistently for mobile users and remote sites. This diagram shows the high-level position of Prisma Access. You see users, whether they are mobile users or remote networks, connecting directly to the central Prisma Access cloud. The cloud then acts as a central checkpoint, inspecting all traffic. After inspection, the traffic is safely directed either to the public internet, to SaaS applications, or towards your private data centers. The enforcement of consistent security rules is a crucial step in this process. By positioning Prisma Access as the single service edge, we ensure that security policies are consistently applied globally, regardless of the user's origin, fulfilling the SASE vision. This cloud-centric model replaces the need for complex, physical security appliances at every remote location. This centralization of security in the cloud, managed by Palo Alto Networks, is what defines the Prisma Access architecture. The flow illustrates the secure paths enabled by the cloud service. This sets the stage for understanding the specific components that manage this traffic flow. Step by step, the architecture routes users to their destinations. To understand the architecture, we must look at both the control tower and the engines. The control tower, where administrators manage everything, is typically the Strata Cloud Manager, or SCM. SCM acts as a single point of glass for configuring various components like Prisma Access agent settings and infrastructure details. Alternatively, legacy or large deployments may use Panorama for management. Now for the engines. These are the security processing nodes, or SPNs, which Palo Alto Networks deploys and manages globally across its cloud infrastructure. These nodes are the data plane components where security inspection occurs. Different types of SPNs handle different traffic. For mobile users, we have MU SPNs. For remote branches, we use RNSPNs. And for connecting back to your data centers or headquarters, we use SCCANs, Service Connection Corporate Access Nodes. These specialized nodes ensure optimized performance for different traffic flows. This separation ensures management is centralized, while security is distributed and always available. What did we learn? We learned the core management platforms, SCM/Panorama, and the physical security engines in the cloud called Security Processing Nodes, SPNs. The important point is that Prisma Access uses specialized nodes, MUSPNs, RNSPNs, SCCANs, to deliver dedicated security functions based on the connection type. Let us focus now on how individual mobile users securely join the Prisma Access environment, building on the concept of the MUSPNs introduced in the previous slide. The primary and recommended connection method uses the Global Protect app, which creates agent-based secure tunnels. When a user first connects, they interact with the Prisma Access portal. Think of the portal as the registration desk. It handles authentication and helps distribute necessary connection settings and the Global Protect agent itself. Once authenticated, the actual user data traffic travels securely through the Prisma Access gateway. The gateway is the actual security inspection point, residing within the MUSPN. For users who don't rely on the Global Protect application, such as those using web browsers or specific legacy systems, the connection can be established using explicit proxy, often configured via PAC files. Both methods ensure the user's traffic is secured by the mobile user security processing nodes. What did we learn? We learned that mobile users connect using portals for initial setup and gateways for active traffic flow, sometimes via explicit proxy. The important point is that all remote user traffic must pass through a Prisma Access component, gateway/proxy, for inspection by an MUSPN. This diagram illustrates the secure user access flow. A mobile user device first connects to the Prisma Access portal for authentication and configuration. The portal is critical for setting up the user session. This connection then transitions to the Prisma Access gateway for traffic handling. Alternatively, traffic can flow via the explicit proxy gateway path. Both connections terminate at the MUSPN, which we established is the node responsible for mobile user security. The MUSPN applies security policies before sending traffic out to its final destination, whether that is the public internet or private applications. The key function here is establishing a continuously monitored and secured channel for the remote workforce. This comprehensive routing structure ensures that security enforcement is achieved immediately upon the user initiating their connection. This is the mechanism by which individual remote access is provisioned. Moving from individual users, we now look at connecting entire sites, like your remote offices and data centers. Remote networks, typically your branch offices, connect securely to the cloud infrastructure using IPsec tunnels. The networking device at the branch, the CPE, establishes this tunnel by peering with a service endpoint address that Prisma Access assigns. This connection terminates at an RNSPN. To ensure that all users and branches can reach internal corporate resources, such as applications in your headquarters or data center, you deploy service connections. Service connections are also IPsec tunnels, but they connect Prisma Access directly to your corporate network edge. Once deployed, the internal routing within Prisma Access creates a secure, full mesh architecture, linking mobile users, remote networks, and service connections, enabling communication between all protected elements. This is how Prisma Access scales secure connectivity for the modern distributed enterprise. What did we learn? We learned that remote networks and service connections use IPsec tunnels, and the latter is essential for connecting users/branches to HQ/data center resources. The important point is that the service endpoint address is the destination IPFQDN used by the CPE to establish the cloud tunnel. This diagram visualizes how Prisma Access integrates remote sites and data centers. The remote network CPE initiates an IPsec tunnel to the RNSPN. Simultaneously, the HQ or data center CPE connects to the SCCAN, also via IPsec tunnels. Once connected, the internal cloud architecture creates a secure mesh, linking the RNSPN and SCCANs. Critically, mobile users, represented here as coming from an MUSPN from slide 3, can now securely access the internal HQ data center resources through the SCCAN. This ensures full connectivity and consistent security enforcement across the entire distributed network environment, simplifying route management for the organization. The service endpoint address is the key public address used by the CPE to locate and establish the tunnel with Prisma Access. Now we transition to the essential concept of IP addressing, beginning with the infrastructure subnet. This address space is fundamental. It acts as the private, hidden network backbone within the Prisma Access cloud environment. This dedicated network is essential because it allows all the core components we identified earlier, the MUSPNs, RNSPNs, and SCCANs, to securely communicate with one another across the global cloud footprint. Due to the large scale of the service infrastructure, you must allocate a minimum of a 24 subnetwork. For example, the default 192.168.255.0/24. It is a strict requirement that this subnet uses RFC 1918 private IP addresses, and, crucially, that it does not overlap with any existing IP ranges in your corporate network or the mobile user IP pools. Overlap will cause significant routing failures. This subnet is managed entirely by Prisma Access, but you define the range during initial setup. What did we learn? We learned that the infrastructure subnet, typically a minimum/24 RFC 1918 network, is the internal communication backbone for all Prisma Access components. The important point is that the infrastructure subnet must be unique and non-overlapping with internal corporate networks or mobile user pools. Following the establishment of the internal backbone, we focus on the addresses given to individual users, called client IP pools. These are the IP ranges from which the Global Protect Gateway assigns a unique IP address to the virtual adapter on every connected mobile device. The default IPv4 pool is 100.127.0.0/16. Careful sizing is needed, as each unique connected device requires its own address. Similar to the infrastructure subnet, these pools must adhere to RFC 1918 standards and must be unique. They cannot overlap with internal networks or the infrastructure subnet. If you are moving towards modern addressing, Prisma Access supports IPv6. However, a dual-stack configuration, IPv4 and IPv6, is recommended. If using IPv6, the client IP pool must allocate a minimum subnet size of /80. This distinction between the internal infrastructure IP space and the external client access IP space is crucial for granular control and routing efficiency. What did we learn? We learned that client IP pools assign unique addresses to mobile devices, enabling them to connect, and they require careful planning regarding size and non-overlap. The important point is that proper IP pool design is essential to prevent internal and external network conflicts. This diagram illustrates the process of client IP pool allocation. The central green box represents the client IP pool, which could be an IPv4/16 or an IPv6/80 subnet minimum, from which addresses are dynamically assigned connecting devices. Every connected device receives a unique IP from this pool. The red constraint boxes reinforce the critical rules for managing this address space. The use of RFC 1918 addresses is best practice, and there must be absolutely no overlap with your internal corporate IP ranges or the infrastructure subnet discussed in the previous slide. These constraints are vital for ensuring seamless connectivity and preventing routing loops or shadowing in the deployment. Adhering to these addressing standards is a foundational requirement for stable Prisma Access operation. When your secured traffic leaves Prisma Access and heads towards the internet or a public cloud service, the outside world sees a public egress IP address. This address is the source IP used by Prisma Access for those outgoing requests. For access to many critical SaaS applications or partner networks, these public egress IPs must be manually added to an allow list by the external party. This is a management overhead, as these addresses are not static and can change when Prisma Access automatically scales its resources, or if you configure a new geographic location. You must monitor these changes proactively to prevent service disruption. Now, concerning addresses you must never use. Prisma Access strictly reserves two key IP ranges for its internal operations: 169.254.0.0/16 and 100.64.0.0/10. Attempting to use these reserved subnets anywhere in your deployment will guarantee network conflicts and must be avoided during all IP planning phases. Understanding these ranges simplifies allow listing workflows. What did we learn? We learned the difference between public egress IPs, seen externally, and ingress IPs, internal to the service, and identified two critical IP ranges reserved by Prisma Access. The important point is that public egress IPs must be tracked and allow listed externally, and reserved IP ranges must be avoided in corporate IP planning. This diagram illustrates the critical role of the public egress IP. Traffic exits the Prisma Access environment using one of these IPs. This egress IP must be allowed listed on external services like SaaS applications to permit access. The diagram also clearly shows the two reserved IP ranges, 169.254.0.0/16 and 100.64.0.0/10. These are strictly retained for the cloud service's internal functionality, such as link local communication and carrier-grade NAT operations, and must be avoided entirely during any network planning phase. Failure to respect these reserved spaces will introduce conflicts directly into the managed Palo Alto Network's infrastructure, leading to connectivity issues. Proactive management of egress IPs is key to maintaining connectivity. Our final specialized IP concept is the loopback IP address. These are internal logical addresses that Prisma Access uses as the source IP when communicating with your internal network resources located in your headquarters or data center. They are critical for accessing internal services, particularly Radius or Active Directory AD servers required for user authentication. As they are internal IDs, they are allocated directly from the infrastructure subnet defined back in slide 5. A key distinction is that while loopback IPs for service connections remain stable, the loopback IPs used by mobile users can change dynamically, particularly after an infrastructure or data plane upgrade. Therefore, Palo Alto Networks strongly recommends that you allow list the entire infrastructure subnet range on your internal servers to ensure continuous authentication and access. Lastly, the routing within this complex environment relies on BGP. BGP uses an autonomous system AS number, such as the default 65534, to dynamically identify and manage routes, ensuring traffic reaches the correct destination efficiently. What did we learn? We learned about loopback IP addresses used for internal communication and the role of BGP in dynamic routing within Prisma Access. The important point is that allowing the entire infrastructure subnet range on internal servers prevents mobile user authentication issues due to changing loopback addresses. This final diagram connects the internal addressing back to routing. The loopback IP is derived from the infrastructure subnet and serves as the internal identifier when Prisma Access needs to authenticate users against internal services like Active Directory or Radius servers. Because these mobile user loopback IPs can change, the internal corporate server must be configured to allow list the entire infrastructure subnet range for reliable access. Finally, the infrastructure subnet helps configure the Border Gateway Protocol, or BGP, for dynamic routing. BGP automatically handles route advertisement and management, ensuring that traffic successfully reaches the correct headquarters or data center network across the global backbone. This comprehensive architecture ensures both secure connectivity and intelligent, scalable routing across the cloud.